Hi there, this is Truth Socrates. Welcome to video number 42, the last video for now for my series on multivariable calculus. And if you're taking my class this semester, you're probably cheering your head off that, oh, finally we have reached the end of our journey, so to speak. So this is video number 42, and if you are a fan of The Hitchhiker's Guide to the Universe, you may have heard of that book, you'll know that 42 is a very special number. So we will be doing one section from chapter 8, the unfinished chapter. We're going to be talking about extremal analysis today. So I'm going to change tab, but I also have to adjust my viewing screen. I'll see you in 1 second. Okay, so extremal analysis is just a fancy term for the process of finding the highest and the lowest points in a graph. Okay? So there are some terms that we need to review from basic single variable calculus. So let's assume that we have a function which is defined on an interval, which is any subset of all real numbers. Okay? So we will call a point, a f of a, on the graph of our function, an absolute maximum point if f of x is less than or equal to f of a for all x in the interval. Okay? In other words, f of a is the highest possible value for the function. Any other f of x will be smaller than that value. Okay? So we also say that our function has an absolute maximum at x equals a, and f of a is the absolute maximum value for our function that our function attains on that interval. Okay? So take note of the pronouns. This is an absolute maximum, because there could be more than one. But we have the absolute maximum value because that number, that greatest score, is unique. Okay, you can't have two high scores, right? One of them will be lower than the other, or they're exactly the same. Okay? So we also call our point an absolute minimum if the inequality is reversed. So this time, f of x is at least f of a for all x in our domain. Okay? So put together, these points are called absolute extrema, which is the plural for extremum. Okay? Mum's the word. All right. So as I mentioned, a maximum point need not be unique, but the value is unique. Okay? Now let's also talk about local extrema, local maximum and minimum points on a graph. Okay, so basically what this says is, if you look near a point, that is the highest point on the graph. Okay, so don't look too far away, just look close by. That will be the highest point that you will see. Okay, so it's kind of like climbing a mountain range. Okay, you reach the highest point. Oh, but if you keep walking, you go downhill again. Eventually, you might be going uphill again, and you might get to a higher peak on the mountain. Okay, so how do you define that? A point is a local maximum on the graph of our function if, again, f of x is less than or equal to f of a for all x in a small interval. Okay, so notice it says a minus c, a plus c. So basically it means starting at a, you move to the left by c and to the right by c. Okay, so it's like to the left by 0.1, to the right by 0.1. As long as you're still inside the domain of your function. Okay? So you want the values of the function to be smaller than f of a within this small interval. Okay? And again, by reversing the inequality, you get what we call a local minimum point. Okay? So here's a good example to start with. Something very familiar, just the cosine function. Okay? So we know the range is from -1 to 1, the domain. All real numbers. Okay, maybe I should have started there. Okay, but the highest value that you will get is 1, so that is your absolute maximum. The lowest that you will get is -1. That's your absolute minimum. Okay, so we know from trig that the absolute maxima occur at 0, 2 pi, 4 pi, and so on, and -2 pi, -4 pi, and so on. Those are the even multiples of pi. Okay? And the minima happen at pi, 3 pi, 5 pi, pi, negative 3 pi. Those are the odd multiples of pi. Okay? So we can formally say that the absolute max happen at 2n pi 1, where n is an integer, and the absolute mins happen at 2 pi, that should be 2n minus 1 pi, negative 1. Okay, whoa, real edit there. Okay, so we can also, however, restrict the domain of our function. So what if we restricted our domain to negative pi, 5 pi over 4? Okay, so the graph is only up to here. We don't even reach pi. We don't even reach negative 1. Okay, so as we can see, this time the absolute maximum is at the same point, 0, 1, that we've seen before. But the absolute minimum is now here at 5 pi over 4, where cosine of 5 pi over 4 is negative 1 over radical 2. Okay, so we still have a local maximum, but this time we don't have a local minimum. Okay, so there's a technical reason for that. Okay, we said there should be a small interval over here near 5 pi over 4, where that interval is still inside the domain. Okay, but our domain is smaller now. We only go from negative pi to 5 pi over 4. So no matter how small you make an interval centered at 5 pi over 4, you will always go over. Okay, so therefore, this point is an absolute minimum, but it is not a local minimum. Okay, so that was fairly easy, but what if you have something more complicated? Okay, so let's review what we did in single variable calculus. And of course, there are derivatives involved. Okay, let's assume for simplicity that we can compute both the first and the second derivatives. Okay, so therefore the first derivative is automatically continuous. Okay, so I hope you remember we look for critical points. Okay, and that is where the derivative is 0. All right, now why is that? Suppose you have a local minimum. Okay, then the derivative has to be 0. Okay, why can't it be positive or negative? Well, if it were positive, then near that point, the derivative will stay positive. Okay, that comes from the continuity of the derivative. Okay, but what does a positive derivative mean? You have an increasing function. Okay, so you're somewhere here and your function is doing this. So there are points above you, there are points below you. That's not a local max or a local min. So the derivative can't be positive, it can't be negative either. You can't be doing this. Same reason. There will be points above you, there will be points below you. Okay, so the derivative has to be 0. And those are called our critical values. Okay, all the values of C where f prime of z is 0, or more generally undefined. Okay, but we're going to stay away from that because it's complicated enough when the derivative is 0. Okay, how can you tell if you have a local max or a local min? Okay, we have what's called, what's called the second derivative test. Okay, so you find the second derivative at that point C, and if it's positive, you have a local maximum, and if it's negative, you have a local, you have a local minimum if the derivative is positive, and you're switching it up. And you have a local maximum if the second derivative is negative. Okay, how did I know I was switching it up? There's one function you should always think about when you're doing the second derivative test, and maybe your basic calculus teacher told you about this. X squared. Just think about x squared. You cannot go wrong. X squared, the parabola. Okay? First derivative 2x, second derivative 2, constant. The second derivative is always 2. It's always positive for x squared. Okay? What is the vertex for x squared? It's a local minimum. Okay? So when the second derivative is positive, at the critical point, you have a local minimum. If it's negative, upside down x squared, negative x squared, your second derivative will be negative. Okay, So we did one more thing in basic calculus, and that was if you restrict your function to a closed interval from a to b, and your function is continuous, then you are guaranteed to have both an absolute maximum and an absolute minimum. That's called the extreme values theorem. Okay, so how did we do that? Let's review the algorithm, and I'll show you an example. You look for the critical points. Okay, so keep your fingers crossed and hope that your function is differentiable. Okay, where's the derivative 0? So you find all of the points where the derivative is 0. And then you make a table of values. Okay, so you put those values in that table. You include the endpoints a and b. Okay, plug in those numbers into your function. Look for the high number, look for the low number. Boom, you got your absolute max and your absolute min. Okay, so let's zip through this example. I'm not going to talk about all the details, but here we have a 4th degree polynomial. That's quadratic, multiply it out to degree 4. Let's look for the first derivative. You know the product rule, you know the chain rule, you'll get this. I checked this with Maple, so no mistakes in this one. So that's 0 at -3. Use the quadratic formula here. You get these two real numbers, so you have 3 critical values. Now we get the second derivative. So starting from here, again apply the product and the chain rules, and then you get this. Okay, so we have that second derivative. We're going to plug in these 3 numbers into that second derivative. Okay, now that's an ugly irrational, so we will approximate them because we only care about positive or negative. Okay, unless your answer is really close to 0, you don't have to worry about round off errors. Okay, so plug in the critical values, you will get these for the second derivative. So that's positive 16, positive 27. So these two, what did we say? When your second derivative is positive, you have a local minimum. Okay, and if it's negative, you have a local maximum. Okay, so let's take a look at the picture. Ooh, there we go. So you have a local minimum at -3, and at that radical something, this guy. Okay, and we have local maximum at this point. Okay, now what about absolute minimum maximum? Okay, well in this case you have a degree 4 polynomial, so that's going to go to infinity, that's going to go to infinity. Once you have all the critical points, you're done. Okay, it's going to be decreasing on this interval, increasing on this interval. So this is your absolute minimum. Okay, is there an absolute maximum? Nope, but you do have a local maximum. Okay, so while we have this picture up and running, we are going to restrict our domain to -3.5, which is somewhere here, up to -1.5, which I think is somewhere, no, it's too small for me to see, somewhere there. Okay, so we're going to look for the absolute maximum and minimum of our function within that interval. Okay, we had a total of 3 critical values, but one of them, positive 0.281, that's outside this interval, which is entirely negative. Okay, so we don't include that point in our table. Okay, we include the -3, the -1.781, and the 2 endpoints, -3.5 and -1.5. Okay, we plug in those 4 numbers one at a time into our original function, not the second derivative this time, the original function. Okay, so we get these 4 numbers. Think of them as scores. Okay, you have 4 contestants, they're over here. They get these 4 scores. Okay, so who has the high score? Looks like 3.227 is the high score. So this is our absolute maximum. There it is. And the biggest loser with a low score of 0, no negative scores. So 0 is our low score. That belongs to x equals -3. All right, so let's see equivalent definitions for a function in 2 variables. Okay, so this time to specify a point, we need x, y, and z. Okay, so we will have a, b, f of ab as a point on the surface, which is the graph of our function. That point is an absolute maximum point if f of xy is at most f of ab for all points xy in the domain D. Okay? So we also say that your function has an absolute maximum at ab, and f of ab is the absolute maximum value that your function attains on your domain. Okay? Again, flip the inequality, you get absolute minimum points. Okay? And put together, you have absolute extrema. Okay? What about local max and min? Okay, so the same point is the local maximum point on the graph if, again, f of xy is at most f of ab for all xy in a small disk centered at ab, which is still within the domain of our function. Okay, so more briefly, we say that ab is a local maximum. Okay, so within that little circle, that little disk, your function is below that value, f of ab, or it attains that value at your maximum point. Okay, and again, by reversing the inequality, you have a local minimum point. All right, so one easy way to understand this is with this simple example. And you see squares there, and if you complete the squares, you get something here that should look familiar. It's an elliptic paraboloid. Okay, so this function is just an elliptic paraboloid. We can read off the vertex, remember? When x is 2, y is negative 4, these become 0, so your z value is 6. Okay, so that is the vertex of your elliptic paraboloid. And of course, that point is not just the absolute minimum, it is also a local minimum. Okay, it's like the vertex of a parabola. Okay, is there an absolute maximum? Nope. And could there be a local maximum? We will verify that in just a little bit. Okay, so now we want a three-step algorithm, just like we saw for a function in one variable. And the first step is to define critical points. Okay, what are critical points this time? We call them critical values for a function in one variable, but this time we need an x and a y coordinate. Okay, since we need two coordinates, we need a point. Okay, so how can we make a critical point? What does it mean? Well, we're looking really for local maxes and local mins. Okay, so let's say you had a local min, like the vertex of that parabola. Okay, what's going to happen? Well, if you slice the surface at that point with a plane parallel to the xz plane or the yz plane, okay, remember we did this when we talked about partial derivatives. Okay, so you get a curve. All right, you get a cross section of your surface, and because that's the local min, your cross section should look like a local min as well, in 2 dimensions, not 3 dimensions. Okay, so you're back to basic calculus. The derivative here has to be 0. Okay, but wait a minute. What kind of derivative do we get when we fix one variable to be a constant? You get a partial derivative. Aha! So therefore, we are looking for the points on our surface where the two partial derivatives are both 0. And again, we're going to stay with the case where the partial derivatives exist, so therefore they must be 0. If they don't exist, you got a big problem. Okay, we're not going to go there. Okay, so let's go back to the paraboloid. We were able to cheat because we know how to complete the square. Okay, well, what if you forgot? Shame on you. Let's look at the partial derivatives. Okay, so partial x, we get 6x minus 12, nothing else. Partial y, we get 8y plus 32, nothing else. Set them both to 0, so x has to be 2, y has to be negative 4. Oops, 2, negative 4, that was our vertex. Okay, so that's the only critical point that you can have because you have to satisfy both conditions. Okay, you can't say, oh, x will be 2 and y can be anything I want. No. Y has to be -4 as well. Okay, so you have only one critical point, the vertex. There is no local max. We only have this absolute min, which is also a local min. Okay, now more generally, okay, let's add a term to our elliptic paraboloid, except I lost the x, I lost the y. Let's put in an x squared y term here, okay? So when you take the partial with respect to x, you'll get 8x, 0, 6xy. Okay, there we go. Partial with respect to y, 0, 12y plus 3xy. There you go. Okay, both of those have to be 0. Oh no, well, those are not linear equations. So it's not very obvious how we should attack this, okay? When this happens, usually the zero factors theorem becomes very relevant, okay? What is the zero factors theorem? If you multiply two things and you get 0, one of the factors had to be 0, okay? So this is the equation that's easier to attack, okay? That square kind of scares me. The x here we can factor out along with the 2. Okay, so if the product of these two things is 0, then either x has to be 0 or y has to be -4/3. That gives you two cases. We're going to perform a case-by-case analysis. Not very difficult. Okay, so when x is 0, then we have satisfied the first partial derivative equation. But for the second one, you'll get 12y is 0, y is also 0. Okay, so we get one critical point, 0, 0. For the other case, when y is -4/3, now we have to satisfy this, plug in -4/3, that's going to be -16. Yes, so move it to the right, you're going to get +16. Solve for x, you get two possible values. Okay, so you'll get ±4/rad3. Okay, will these be local max or local min points? Okay, well, we need a second derivative test. Coming right up. Wow, it perfectly fits. Here is the second derivative test for functions of two variables. Okay, so look for the points on the domain where the two partial derivatives are 0. We have our critical points. Then what are we going to do? We're going to find the value of AB at this funny looking expression. You take the second partial derivative fxx multiplied by the other second partial derivative fyy, pure x, pure y, and then you remember the mixed partial derivatives fxy. We also have fyx. Okay, and if you're peeking a little bit down here, oh, wait a minute. You have this times this minus something squared. Okay, one way to remember this is to put fxx here, fyy there. You're going to multiply these two together. Remember determinants? Back in chapter 1. We're almost going full circle. fxy squared. What is fxy squared? Well, if the second partials are continuous, and they will be, Clairaut's theorem tells us that fxy and fyx are actually equal. We'll verify that in the example. Okay? So when you multiply these two, it's essentially fxy squared, and you subtract from fxx, fyy. Okay? So this matrix, 2 by 2 matrix, is called the Hessian matrix of our function. And so this expression is called the Hessian determinant of our function. Fancy, isn't it? Okay. How do we use it? Well, there are three possibilities. Okay. If your Hessian is positive, there are two sub-possibilities. Look now at the pure fxx. Okay. If it's positive, you have a local minimum. Sounds familiar? If it's negative, you have a local maximum at that point. Okay. If your Hessian is negative, unfortunately, you have what's called a saddle point. Okay. I shouldn't say unfortunately, because it's still information. Okay. that will literally look like a saddle, as we're going to see in our pictures, okay? It's neither a local maximum nor a local minimum point, okay? So it's just something that shows up when we perform the computation sometimes. Okay, so back to our last example. Here is our function. We took the first partial with respect to x, with respect to y. Now we need the second partials. fxx, we get 8 and 6y, okay? From the same fx, now we take partial with respect to y. 0, 6x, okay? Just to be sure, let's look at fy and take partial of fy also with respect to x, okay? So now you have both xy and yx, okay? With respect to x, that's 0, but you will get 6x also, confirmed. Okay. If you got different answers, check one of them has to be wrong. Okay. So now, how about fyy? Take the derivative with respect to y. We're going to get 12. Okay. Hessian. We need fxx times fyy. So 12, 8 plus 6y minus fxy, quantity squared. So 6x quantity squared. That's 36. We got a 12. We can factor out the 12. And we get minus 3x squared, okay? So if you're doing this in practice, really what we need is just this factor. The 12 we could actually ignore, okay? But I put it in the table anyway. If you leave it out, certainly we will forgive that. Okay, so these are the 3 critical points that we found in our last example. We will now plug them into the Hessian. Okay, so I just rewrote it with a and b instead of x and y. Okay, so remember it was 6y minus 3x squared. Okay, so fortunately when you square the x, the radical 3 goes away. Okay, it just becomes 3. And they get the same score because that is a square. Okay, so you get 2 negatives here. The test says those are saddle points. Okay, but that's positive. So now we go to either a or b. Look at fxx at 0, 0, okay? So fxx was 8 plus 6y, okay? So 8 plus 6y, you're going to get 8, which is positive. And when it's positive, we get a local minimum, okay? So we have some pictures over here. Kind of looks like a mask for a superhero, right? So I was tempted to spin it for a second there. Nope. These are static. They're not going to move. Okay. Notice that the surface is symmetric across the y-axis because of the x squared. Okay. There, you only see x squared. You don't see x by itself. Okay. So there's symmetry, and the 2 saddle points are here, and 0, 0, 5 is our absolute min. I'm sorry, our local min, which we can verify is right there. Okay. And these 2 are saddle points. So, you know what, let's go to GeoGebra because I still have it over there. All right, so there it is. So I plotted our 2 saddle points. And the local min is on the z-axis. So there you see it, okay? See how it's like a low, it's like a cup at that point. So think of it as if you pour water, it's going to collect at that point. It's like the vertex of a parabola, sort of, right? Now, what about this saddle point? Okay, this is one saddle point, and we have the other saddle point over here, symmetric across the y-axis, okay? So if you look from the bottom, we have, there's a saddle point over here. If you look from the bottom, it looks like a maximum, doesn't it? Right? But if you look from the top, there's the same point. Now it looks like a minimum. Okay? So that's weird, right? From one perspective, it looks like the highest point. From another perspective, it looks like a lowest point. Okay? So that's what makes it a saddle point. There was a quadric surface that we saw in chapter 1, which behaves just like this, okay? And it was called the hyperbolic paraboloid, okay? It's almost exactly the same idea, Okay, so of course the same thing happens to this saddle point. They're symmetric. All right, so now we're ready to complete the algorithm. Okay, we need the third step, and that was back for single variable. If you have a continuous function of closed interval, you look for the points where the derivative is 0. You make a table, and then you include the endpoints in that table. Okay, slightly, who am I kidding? It's more complicated for a function in two variable because we don't have endpoints. We have boundary points. We have edges. Okay, so the simplest domain that we will look at is a rectangle. Okay, so a rectangle has 4 sides, 4 edges. Okay, so what does the extreme value theorem say when we have a continuous function on a domain such as a rectangle, which is closed and bounded? Okay, so more generally, when we were performing double integrals, remember those domains, type 1, type 2, those are closed and bounded domains as well. Okay, so you could have a disk, you could have a quarter disk, you could have a triangle, you could have a parallelogram. Those are all valid closed and bounded domains. Okay, the disk and everything inside it, for example. Okay, the extreme value theorem says that if you have this continuous function and your domain is closed and bounded, then once again, you will get an absolute maximum point and an absolute minimum point somewhere in the domain. But exactly where they are, the theorem doesn't tell you. Okay, we have to look for them. These points could be in the interior of the domain, or it could be one of the boundary points of our domain. It could be a corner, okay, or it could be just a point on the edge, not necessarily a corner. Okay, so just about anything goes. Okay, and it's the boundary that will take up time. But I'm going to give you a function though where it's actually going to be not so complicated because of the nature of that function. Okay, so let's take a look at that example. Whoops, my bad, got ahead of myself. Okay, before we do the example, what are we going to do? Okay, so this is the algorithm that will find for us the absolute max and min of our function. Step 1, look for the critical points. Okay, so we did this. Solve for when both partial derivatives are 0. Okay, then we're going to make a table. Okay, we're not going to apply the second derivative test because we're looking for absolute max and min. We're not looking for local max and min. Second derivative test finds you local max, local min. Okay, we don't want those. We want to be absolutely highest and absolutely lowest. Okay, so we're going to start a table and we're going to put all the critical points that we found, which are within the domain. Okay, we're going to find the value of those points at the original function, f of xy. Then, take a deep breath and then work on the boundary. Okay, if this were a rectangle, okay, and we're going to do the rectangle in a while, we're going to parameterize each edge, plug in the parameterization into your function. That will give you a function in one variable, p. It's a composition. Okay, so we're back to single variable calculus, what we did in the introduction. Okay, so we can now find the critical points of this restricted function, g of t. Where is that derivative g prime at a point equal to 0? Okay, now, because in the single variable algorithm, you include the endpoints, that basically means that the corners of your rectangle are included. Okay, so when we do the example, we'll go ahead and throw in the corners as well. Okay, so you repeat that for every edge, every curve on the edge of your domain. Okay, so you might get a lot of critical points. Okay, we're going to put them in a table. Find their scores by plugging them into your function. Look for the highest score, that's your absolute max. Look for the low score, that's your absolute min, and the story. All right, so here is our example. It's cubic. We've been upgraded, okay? We will restrict it to the rectangle -2 to 4 and 0 to 4, okay? What are the partial derivatives? 3x squared minus 6x minus 9. These all turn to 0, okay? That can be factored, factor. So the zeros are at -1 and +3 for partial of f with respect to x. Repeat for partial of f with respect to y. 0, 0, 0, minus 6y squared plus 42y minus 60. Factor further. And our zeros are at y equals 2 or y equals 5. Okay? You only need to make one of them, one of those factors, 0. Okay? Now, you pick one number here, one number here. Okay, you have two choices here, two choices here. You have a total number of 4 combinations. So we have 4 pairs of value that we will plug, that we will consider. Okay, so we have these 4 points. However, here's our domain. Remember, it's -2 to 4 and 0 to 4. Are you in there? -1, 2, yes. -1, 5, no. -1, 5 is somewhere here. 3, 2 is over here. Fine. 3, 5, no, you're up there. Okay? So only these 2 points are valid contestants. We reject -1, 5 and 3, 5. Okay? So we can start our table, and it will include the 4 corners of our rectangle. Okay? -2, 0, -2, 4. There they are. And +4, 0, and +4, 4. There they are. Okay? Plug in those numbers into a function, not the second derivative, the original function. Okay? Here are the numbers that we're going to get. Okay? So again, it's a contest. We're looking for a high score. We're looking for a low score. Okay? Sad to say, everyone has a negative score. Okay, but doesn't matter. They're just numbers. So, the lowest negative score appears to be -79, and the highest negative score appears to be -2. Okay, so we can ignore the first pair and these other pairs. Okay, so now for the not so fun part. Okay, we'll parameterize each edge of the rectangle. Let's start at the bottom. Okay, so that's from -2 to 4 on the x-axis. Okay, so y is 0, and x is just t. T goes from -2 to 4. Okay, so we plug this parameterization into our function. So x turns into t, y is 0, so it just disappears. Okay, get the derivative 3t squared minus 60 minus 9. But wait a minute. Partial f with respect to x was 3x squared minus 6x minus 9 because we just changed x to t. Okay? So therefore, we get the same critical points that we had before, which were -1 and 3. These are the t values now, but they're still x values because t represents x in this parameterization. Are they both inside our interval, our bottom edge? Yes. So we get 2 critical points on the bottom edge, which will be thrown into our table. Okay. So for the top edge, we do the same thing, but instead of at 0, our y is now at 4. Okay. And then we get a similar restricted function, but again, when you get the derivative, you'll get the same derivative that we have before, and that's because these are all constants. They just disappear. Okay, so again, we get -1 and 3 as our critical values. Y coordinate is at 4. Okay, now we go left and right. Okay, so on the left, our x is -2. Our y goes from 0 to 4. So y is just t. And we plug in -2 into x, t for y, and we get the derivative again. That looks familiar. That's the partial of f with respect to y. Okay, so we saw that the critical values there are 2 and 5. And are they both inside? Oh, wait a minute. T goes from 0 to 4, so only 2 is inside that interval. 5 is rejected. Okay, so just like we rejected those 2 points, they were not in the interior of our domain. Okay, so we repeat for the right edge, and again we get the same critical values, only t equals 2 is within our domain, so this time our critical point is at 4, 2. Okay, so now we have 2 plus 2 plus 1 plus 1, 6, a total of 6 critical points that we will add to our table. And again, we deleted all the scores that we had earlier except for what was the current loser and the current winner. Okay, so we have these 6 new critical points on the edges. We will still call them critical points. And we get their scores. Okay, so plug in these numbers into your function, and we get these numbers. Oh, finally somebody got a positive score. Okay, so it looks like that is the absolute maximum. And do you get to keep your crown, the biggest loser? Yes, because that negative 72 is not enough to beat negative 79 for last place. Okay, so we can of course plot those points in GeoGebra along with the surface. Okay, and we'll go there in a minute. Okay, now before we leave this example, let me just tell you that the derivatives were easy along the edges and familiar because that's just a function in x only. That's just a function in y only. Okay, so when you take the partial of f with respect to x, you just get p prime of x. And when you get the partial of f with respect to y, you'll just get q prime of y. Okay, so these were what we were calling g of t earlier, except, I use t as a parameter just because that's my habit. Okay, if you want to use x and y, that's entirely up to you. Okay, I certainly won't complain. All right, so here we are. This is a different GeoGebra. So I have plotted the surface over here. Ignore the over one there. What I want to show you is how to adjust the scale on the z-axis. Okay, what I was doing earlier when I was kind of designing this, I thought, you know what, I'll divide it by 50 so that I don't have to move the z-axis. But I think it would be good for you to learn how to manipulate that if you've never done it before. Okay, so this is the standard view. Okay, so notice that it's 1, 1, 1. Okay, so you can barely see anything. I have plotted the 3 extreme points. Okay, we have the biggest loser and the runner up. Okay, and here is the absolute maximum. Okay, you can see the absolute maximum, but not these other points because negative 72 is way, way, way below. Okay, so now what do? You take, you go here, and then you click on that, and you go Move Graphics View. Okay, so notice that you see this thing here that looks like a spindle. You use it to grab your z-axis, and then you push down. Okay, so notice that you're seeing more. Okay, but the problem now is your surface is way below. Okay, so after we do that, okay, we are going to lift the xy plane. So I'm going to try that again because I was pushing it. Okay, there you go. Okay, that's better. The origin is not moving this way. Okay, so we're seeing more. There you go. We're seeing more of the negative portion. Keep going. It's like we're pumping it. Okay, there we go. Now we're seeing what the surface actually looks like. Okay, so I'm going to pause it because I need to move my viewing recording rectangle over to the right. So there we go. So now we can see the entire surface on the entire rectangle. Okay, so if you look at it from above, you will get a rectangle. We can see the absolute minimum point, which is over there. The runner-up is close behind, but not quite enough to be lower than that point. Okay, of course, numbers don't lie. And that is, of course, also the absolute maximum point on our surface. There we go. We are finished with Math 5C. So I hope you enjoyed this video. I can't exactly say I'll see you next time, but hopefully when the pandemic is over and we're back in school, we'll see each other in person. So until then, enjoy the rest of your day.